Good morning, good afternoon, or good evening, wherever you are. Thanks very much for joining. I appreciate your time today. My name is Gareth Noyes, and I'm the Chief Strategy Officer at Wind River. I'll be hosting the session this morning. For the next 30 or 40 minutes or so, I'll be talking about the challenges of digital transformation focused on the new intelligent edge. Now, the edge is very different to traditional IT and cloud-like computing infrastructure, and I'll be delving on those differences. In particular, I'll be diving into the key drivers for digital transformation, and I'll highlight the unique challenges presented by critical edge infrastructure. So I'll outline new design dynamics you'll need to consider to be successful in this digital world, and I'll touch on the key skills that you and your organizations will need to develop to be successful in this transformation. And after that, we'll open up for questions. So let's dive right on in. So the world is digitally transforming. This likely isn't news to you. In fact, this journey is in full swing on the IT side of the house. So although computers have been around for decades, I think the internet boom of the late 90s, which drove ubiquitous connectivity, and the advent of cheaper computing that was much easier to use, enabled businesses to evolve and adapt the way they think about their business. Whether it was interacting with online with their customers, tracking inventory, or focusing on streamlining their businesses through process optimization, or sometimes just automating tasks that were previously carried out by people. That transformation is pervasive across businesses, industries, and geographies, and only seems to be accelerating due to COVID. In fact, COVID seems to have poured both fuel and oxygen onto this transformation, and its pace has rapidly accelerated this year. So it's not a question of if you transform, it's about how you transform. Focusing on managing digital transformation is really critical, and it's actually a constant topic of conversation for most executive teams. In fact, 68% of publicly traded companies report progress on digital transformation during their quarterly filings. And many organizations have created specific exec roles with a seat at the top table focused on digital transformation. And those companies that do have a chief digital officer are as much as 54% more likely to be successful in digital transformation than their peer organizations who don't. And so I think this is a recognition that digital transformation is real and part of everyday business. It's happening. It's been executed, managed, and measured, and specific executives have been given mandates for its success. Now, what you do to embark on digital transformation may vary from organization to organization, but the fact remains that it is a focus of business life. The majority of digital transformation efforts today are focused on things like business process or supply chain optimizations, basically automating and linking together business systems to digitize processes, often replacing humans or manual tasks. But soon there'll be 7 or more IoT devices for every human on the planet. That's a very device-rich future. Edge devices are increasingly becoming a much more important part of the digital world too. And the mandate to digitally transform is shifting from a people-centric to machine-centric focus. And as we undergo this change, the way that we design, build, test, and deploy these machines and devices is also going to have to change. In fact, Michael Gale, an expert and leading author on digital transformation, goes as far as saying that digital success should be the #1 focus as we modernize our development processes for our organization's embedded technologies, which is critical at the edge. As I've mentioned, digital transformation is alive and well in IT, but the next frontier for innovation and transformation is happening at the edge. Now, the edge to me is the computing located at or close to the source of data. It's all the physical devices embedded in the world around us, whether it's cell towers connecting you to your cell phone as you roam around the countryside, or it's the ECUs in your car that are providing basic drivetrain control systems or enhanced driving features, or equipment managing the flow of traffic, keeping you home safe, or flying you to visit loved ones. But it's basically all the computing that you can physically see around you. You get the gist of it. Anyway, the edge is computing software that happens in the real world. And as computing gets cheaper, smarter, smaller, it becomes more and more ubiquitous in the environment. And it's not just the computing itself that accelerates its deployment. It's the advent of faster and more reliable connectivity. In fact, we're on the cusp of a connectivity revolution with the launch of 5G in many markets in the next couple of years. And as consumers, we tend to think of 5G as a generational evolution from previous 3G and 4G standards. But there are a couple of key differences with 5G that will accelerate rather than some machine-centric edge infrastructure. And the first of that is scale, massive machine scale, being able to service billions of endpoints with 5G. And the second characteristic of 5G that's incredibly interesting is its quality of service that will bring low latency and extreme reliability to wireless and really enable the flood of data at the edge produced by all the billions of IoT devices that are around. So the proliferation of computing devices and seamless connectivity means that the edge is where the majority of data will be processed in the future, and not too distant a future either. In fact, Gartner claims that 80% of all data will be processed at the edge as soon as 2025. Now, this is in stark contrast to early views of IoT architectures that saw sensors and devices connected to the cloud via gateways. And in those generic topologies, we saw most of the data being pushed northbound to the cloud. And in fact, that's been turned on its head. And we've now realized that we need to move the computing to the source of data, which is being generated and needs to be processed at the edges. So whereas the cloud has given us a good roadmap for how to build and deploy software effectively and at scale, the edge it's very different. It's not like a data center. So in a data center, hardware is fairly homogeneous, and that's changing, by the way, to embrace workload acceleration for AI and so on. So we see more FPGAs and GPUs and things emerging in the cloud. But the edge actually today is very heterogeneous. Devices at the edge are very, very different from one another. And most of them have been designed with specific characteristics in mind or tuned or tailored to very different needs. And in IT and comms, we see things like raw horsepower or throughput be very important. Although at the edge, we see diversity of characteristics that are unique, like latency, determinism, jitter, lots of timing attributes, security, functional safety. And this has led the edge to be in a world of bespoke devices. In tomorrow's world, though, the edge needs to be more adaptable. And while I don't think we'll see a uniform homogeneous environment like today's data centers, I think we will begin to adopt methods of abstraction and isolation that will allow the edge to look more uniform to applications. And this will be enabled by multiple levels of abstraction, whether it's hardware virtualization through hypervisors and virtual machines, or ultimately a fully cloud-native containerized compute model that will allow applications to run seamlessly on your desktop, in the cloud, or an edge device. The truth is, that's not the reality of the edge today, but it's the direction it needs to be headed to handle the scale and complexity of the edge. When you delve into the devices themselves, you see the different problems need to be solved at the edge. So a seemingly very simple but very significant problem with edge devices is the basic security model. So in data centers, physical access to computing infrastructure isn't that much of an issue. In fact, you can handle that easily with locked doors, fences, or badged access to IT infrastructure. But edge devices can be touched and therefore, even potentially dismantled. So even things like leaving pins on a board for JTAG debugging can represent a very real security threat for edge devices that you typically don't have to worry so much about in IT equipment. And devices themselves need to evolve and are becoming much, much more complex. So take, for example, the basic CPU architecture, which has shifted from a single core to multi-core to overcome basic physics that prevented higher and higher power at smaller frequency. And now we're talking of needing to enable multiple compute architectures for acceleration for AI and machine learning. So now devices are much more complex and may contain neural networks, FPGAs, GPUs, or other compute engines. So that diversity of hardware is very significant at the edge and is very different. So with this increasing complexity and being on the cusp of a new generation of 5G networks and a push towards more automation and autonomy, this is going to create a huge deluge of data. And so we need to simplify and vastly improve how software is built at the edge. This creates an imperative for us to fundamentally change the way we develop, build, test, and deploy devices. It's really time to modernize our approach. Now, the need for modernization is being recognized by companies that are successfully digitally transforming. But they also recognize it isn't easy. They know that digital transformation is volatile, creates a lot of uncertainty, is highly complex and ambiguous. But despite the challenges of transforming, companies recognize that they must do so in order to reap the benefits. Now, AI may seem like an overused buzzword to you. Many companies see this as an opportunity to help them drive new revenue streams or solve new problems. AI, in fact, will be an imperative in our data-rich future. And it's not just the new and appealing use cases that drive AI proliferation. Even seemingly mundane or generic reasons, such as lowering costs, are driving AI adoption. It's not just the ongoing march of technology for the sake of it. It's the explosion of edge devices generating mountains of data that are going to force a different approach to development. As I mentioned earlier, the cloud has given us a roadmap for how to develop software efficiently and at scale. In fact, over a third of all developers surveyed are currently building cloud-native architectures, and an additional 30% plan on doing so next year. Adoption of modern cloud methods and architectures is in full swing, and although that's beginning with the cloud, we see that moving rapidly towards the edge. In a recent Eclipse Foundation survey, many automation technologies felt completely unprepared to tackle the challenges associated with smart machine technologies. In fact, top of mind were some of the ones we've already touched upon, including security, connectivity, and what to actually do with the data and how to analyze and collect it. But with those concerns in mind, how do we tackle them? I think it's time to go back to the drawing board and rethink how software is built for the edge. If you look at the way that software is developed for edge infrastructure today, you'll notice there's a very close coupling to hardware. Develops its rate in what I call an edit, compile, debug paradigm that is very manual and focused on iterative and incremental improvements. And different elements of the system are often developed in silos. Development teams often prefer to develop with hardware-in-the-loop systems that gives them the best fidelity for performance in a real-time system. But this approach leads to silo behavior, a sequential approach to development, and a lot of manual development and testing that is harder than it should be to automate. In fact, the current approach leads to a very hardware-centric approach, where design cycles are repeated over and over again. I design the hardware platform, I layer on an operating system tailored to that hardware. Incrementally, I add middleware, applications, and so on. Now, I may have some layers of abstraction in my software that allows my teams to decouple dependencies, but by and large, my development cycle is just a treadmill of one hardware generation and design after the next, layering software until the next design cycle starts again. But we need to change this paradigm and think of software as a constantly evolving stream of value. The notion of building a device once and deploying forever, a build break cycle is what I call it, that needs to change because needs evolve and devices must be adaptable over their life cycle. Now, this may be counterintuitive if your business model is that you monetize each new version of hardware that you release, but it becomes an imperative if you take into account the evolving need for security updates, for example. Or some companies are viewing this as an opportunity to deploy new functionality to their customers after a device has been fielded. In fact, consumer companies in particular have embraced this paradigm. They understand that evolving and improving their products over time can lead to customer moments of joy, which turns into brand loyalty. Think about the loyal Tesla customers, for example, who will endure sometimes suboptimal features, but they know that they'll be improved and enhanced over time. That thinking starts with accepting the notion of edge devices needing a managed lifecycle. To enable our developers to more productively build code and do so frequently to adapt to evolving product lifecycles means that we also need to rethink the basic tools and edit, compile, debug loops. So we need to empower developers to maximize their creativity and enable them with modern workflows, tool chains, and languages. Really allow them to leverage the impact of broad developer ecosystems who are sharing knowledge and best practices. Now, if we look at choices of computer languages, for example, embedded developers have traditionally used low-level languages like C, C++, or Assembler. Newer generations prefer richer and more productive environments like Python or Rust. Rust, for example, would be familiar to C++ developers, but it's taken off in some domains because of the intrinsic security the language encourages. It's like a modern Ada. If we look ahead, we see that low-code or no-code environments will become more attractive and more pervasive. And this will be critical as developers evolve from being computer scientists to domain experts who are using software as a necessary means to accomplish a task. Adapting to the shift in developer capability and preferences is critical. It's not just a matter of domain experts taking over from computer scientists, but actually many companies in critical industries such as industrial systems or aerospace and defense actually voicing concern about their aging workforces and their inability to hire new talent. In fact, when companies are able to hire, they're faced with a younger population of developers who express completely different expectations about the tools and processes they use. So edge development really needs to become more familiar to this new population who are comfortable with Python or TensorFlow, say. With this imperative to change, let me share some of the key design dynamics you need to consider. So first of all, we must break down silos amongst our development teams. This is one of the biggest inhibitors of digital transformation. We've got to evolve where electrical engineers are only part of the team and where optimization of the whole is not sacrificed by the detail. And teams and functions can work seamlessly together. It's going to be about getting teams aligned on solving the big problems and maintaining a system-centric view. Secondly, we've got to stop thinking that our job is done once the device has been fielded. The entire life cycle of the software, from development through to decommissioning, needs to be managed. The build once and ship forever tradition where updates and servicing is someone else's job needs to evolve. In fact, technologies like 5G and other connectivity technologies will make over-the-air updates much more common practice. Then the notion of scale changes when the world has 40 billion devices, or when applications are deployed with millions of lines of code. The bottoms-up approach of laying software breaks down, and the notion of scale becomes redefined. For cloud developers, the notion of scale is second nature, and this is where approaches like containerization and automation were born. Whereas the system view is important, so too is the detail. Edge infrastructure is often critical and deployed in can't-fail scenarios. That means the functionality has to be guaranteed and system uptime is paramount. That places limitations on how systems can be upgraded, for example. We cannot stop the car to change parts. The interplay of individual elements with the overall system must be well understood. And as we move to more data-centric deployments, AI will be critical to extract insights and meaning. In turn, the AI depends on having accurate and timely data that ensures a context is not stale or moment hasn't passed. So real-time notions will have to be coupled to AI systems for a truly intelligent edge. And security has always been a priority. Historically, that's been security of the platform itself. At the edge, physical access to device changes the nature of security. So too does AI, where security means managing the data and fidelity of machine learning models. Building intelligence and adaptability is key for a secure and every moment construct. Today, the edge is largely populated with physical, fixed function devices. Soon, that will increasingly be augmented by cloud-scale infrastructure housed in the world around us, in our cities and municipalities. And as we evolve the way we build physical devices, we must adapt for devices coexisting with cloud infrastructure, and over time, for that distinction between the two to blur. Now, for that to happen, we've got to evolve our development practices so they're more similar across the two, so that ultimately where software is run is going to be a runtime orchestration issue, not a development choice. But our development paradigms aren't aligned today, and we still need to master development paradigms from different computing domains and start adopting best practices from each. Now, we focused a lot on the discussion so far on development. As we've mentioned, we need to expand our view beyond the development phase to extend it into the complete lifecycle. And with that in mind, let's turn our attention to the deployment of software at the edge. As systems become more complex and time to market pressures increase and security models continue to evolve, thinking that deploying products with feature completeness is not practical. Instead, taking a highly secure, minimal viable product to market and making enhancements over time will become more normal. I mentioned earlier consumer examples, and we're starting to see a move in that direction in automotive too, with automotive systems being upgraded overnight. In fact, we're starting to see defense procurements evolve in that direction too. So I've mentioned several times that Cloud Native has given us a roadmap to new methods for software development. In fact, Cloud Native has shown us that it's not only what you build, but how you build it that matters to achieve productivity and scalability. So first of all, Cloud Native is often synonymous with microservices or containers. That's the what. In fact, what is key is the level of abstraction that these technologies enable. By developing software that's packaged in a certain way, it allows the deployment of software to be orchestrated much more intelligently. Secondly, how software is developed is paramount. To achieve scale and efficiency, high degrees of automation are necessary. And so DevOps, or DevSecOps, has become the norm for cloud native and enabled the massive gains in productivity and value creation brought about by the cloud revolution. Cloud native extends well beyond the develop phase. In fact, most cloud native environments, the distinction between the develop and operate phase are transparent, hence dev and ops. The notion of continuous delivery of software is an integral part of cloud native and lends itself to thinking about the complete lifecycle. Cloud architectures often go further, and containers are often immutable. That means they can be completely replaced with a new version, making updates of individual components or services very easy. The broader picture here is that to successfully enable our teams to build solutions for the new intelligent edge, we'll need to enable multiple developer personas, each with a distinct area of interest or responsibility, working together seamlessly through multiple connected workflows, which enable support of the complete lifecycle. So before we draw this session to a close, let's spend a few minutes highlighting some of the skills you need to ensure you nurture within your organization. We've been talking about the need to break down team silos and enable multiple types of developers and ensure they work seamlessly together and are able to collaborate through their task-focused workflows. This means you should be thinking of building a portfolio of skills. So let's review a few important ones. So the first skill should come as no surprise to anyone who's been reading any tech blog or media in the last couple of years. With data and vast amounts of machine-generated data being at the core of digital transformation at the intelligent edge, ensuring you have AI competency across the organization is key. Now, as technologists, we tend to focus on the bits and bytes of technologies, and we tend to think of machine learning frameworks like TensorFlow or PyTorch, being key AI capabilities. They are, of course, but equally important across organizational capabilities, such as the ability to frame the right questions, applying discipline to your G&A processes such that they become data-driven, and ensuring your leadership and management teams are nurturing data across an organization, in addition to managing people or processes. This is where the role of chief digital officer that I mentioned earlier becomes critical. Now, AI and machine learning are not valuable without correctly curating your data. You'll need to ensure not only that you're collecting the right data, but that it is timely and with the right context. Data doesn't always age well, and the benefit of doing more processing at the edge is because that's a context-rich environment. A massive data accumulated in the cloud may be easy to store, but it may become a nightmare to mine. So designing a system with data at the forefront of your architecture is paramount, and it can't be left as an exercise to the user. The vast scale that comes from richer, intelligent edge, whether it's the number of devices or nodes that's growing, or the vast amounts of data being generated, means that automation of deployed systems is paramount. Now, many systems deployed at the edge today are already automated, and those are often evolving to become more autonomous. Similarly, the process by which we build, test, and deploy software needs to become increasingly automated. Today, a lot of software development and testing steps include some manual processes or necessary interventions by engineers. Now, to address the new intelligent edge, the develop, test, deploy paradigms need to be fully automated. It's about getting teams aligned on solving the big problems and maintaining a system-centric view. Now, earlier I've mentioned that initial IoT architectures favored moving data to be processed in the cloud. But because of cost, latency, bandwidth, a whole host of other issues, we saw that processing is increasingly being done at the edge. That doesn't mean that devices and infrastructure are independent of each other. In fact, sharing of information and context across the edge is very important. So connectivity is key. And in addition to proprietary bus protocols we see in many verticals, IP networking is still relevant and growing as a backbone of many topologies. We see, for example, that protocols such as TSN or time-sensitive networking are emerging as important standards in critical domains. All of these based on an IP foundation. We also spoke earlier about the edge being different from the cloud. A big part of that difference is the diversity of hardware and computing environments. So while there's a move amongst software developers to high levels of abstraction, whether it's frameworks and programming languages or no-code, low-code programming, the reality is that the edge is comprised of physical devices that look very different from one another. Understanding these differences or concepts, such as how operating systems work, for example, will still be valuable and will set you apart from the crowd. Amongst the diverse edge environments will also be mobile devices. Not only are they ubiquitous from our personal and professional lives, but they're evolving to become the interface for interacting with edge equipment. For example, field or service personnel are using augmented reality to automate aspects of support. So architecting the mobile experience into this rich environment is something that needs to be considered as part of your overall design. Interacting with intelligent systems through mobile devices is only one aspect of the user experience. So due to the rising complexity of systems and diversity of experience of those using the systems, from experts to non-experts, building intuitive and easy to use interface is going to be paramount. And let's face it, outstanding UX isn't always best left to a bunch of embedded engineers. Luckily, there's a growing recognition of that being the case, and UX expertise should be part of your team's skills portfolio. Now, this list of skills isn't ordered in importance. Otherwise, you'd have expected security to be close to the top of the list. But information security and security generally is raised as a key concern in most developer surveys. And the need for security expertise persists as much as its scope expands. In fact, developers not only need to know about the key building blocks in technologies such as SSL, or development best practices like secure development lifecycle, or security-focused testing approaches like pen testing, but they also now need to be aware of compliance to standards such as NIST 853 or IEC 62443 that are attempting to apply some uniformity of requirements to the landscape. So all these aspects are important in order to have a good security model. Now, focus on collecting, moving, and storing all the data from systems is important, but knowing what to do with it is critical. So knowing what pain points or use cases you're addressing for your customer, and therefore what data you need to collect and what signals to look for, is all part of you delivering your business value to your customer. So don't lose sight of those problems and which customers you're serving. In fact, raise your nose away from your keyboard and take time to reflect on this regularly. Finally, one of the themes that we've hit on several times today is the need to break down silos. Specific expertise is important, but so is a diversity of expertise. The world is becoming more complex, and we can't expect a single individual to amass all the skills to solve every problem. Increasingly, we need to think about a diversity of talent and skills distributed in teams across geographies. If there's anything this COVID experience has shown us, it's the need to perfect collaboration across digital boundaries. So we've gone slightly faster than I'd expected, and we've come to the end of the presentation today. I'll leave you with a few thoughts though as you digest the content of the material we shared. Digital transformation is happening. It's already here and in full swing in IT, but it's rapidly expanding to the intelligent edge. And as that happens, systems become more and more complex, and we need new ways to adapt to this complexity. So combining skills, tool chains, and methods from both cloud environments and embedded domains becomes increasingly important. And we need to rethink and retool how these systems are built. So helping you succeed on that journey is Wind passion and focus. So we're here to help. With that, I'd ask participants to submit any questions they have in the Q&A button. If you could, it should be at the bottom of your screen. I'll give you a few minutes to submit some questions. Okay, so do you see any industries adapting more quickly to the new design paradigms you covered? So yes, I think there are some sectors that are embracing these paradigms more quickly. I think one is the rollout of 5G in a telco network is really fundamentally shifting that sector from being a hardware-centric deployment model where routers, switches, radio access networks, and so on are physical devices. And they're shifting those to being more software defined. And so the notion of automation of software and applications, of continuous deployment, continuous delivery, really a blend of what is historically bespoke networking equipment and now starting to look like modern cloud equipment. We very much see that being rolled out in the telco market due to 5G. Now, we also see fundamental differences in automotive software, for instance, with higher levels of autonomy. Systems are becoming more complex, and being able to build a fully functional field of devices that isn't changing, it requires these different types of capabilities that I've been talking about. So automotive, we see as well. Interesting enough, we actually see it across all the domains. So aerospace and defense, for instance, there are big initiatives by the US Air Force in the US and the DoD to create software factories, apply high degrees of automation. So I'd say the themes that we've been picking out today are thematic across all the industries that we serve. Hey, Don, nice to see you online. I see you have a question, which is, how do we reconcile the need for adaptability with high availability? Now, I think that's a super interesting one. And I think I often look to domains that have successfully moved through this transition. So if I think about how enterprise IT software has been developed, in the past, there was more of a serial approach to software development where you had an internal test platform, then you had a release platform and a staging area, and then you had a production environment. So you had three platforms, for instance. And what they found is that by applying automation and a lot of very close coupling between the development and the testing, that the testing and adaptability becomes an ongoing part of the process. So I'd envisage that we're going to move to that same paradigm of continuous delivery in high availability systems, but with a few tweaks. So we're going to need failover paradigms to have 5, 6 nines of availability. You're going to have more failover modes. But I think once we start applying those paradigms to more rigid base platforms and apply the tooling and the methodologies, we'll see that applying these principles to higher availability systems is going to become more and more the norm. Now, I think as a sub question that you haven't framed that I think becomes more interesting is, how do you do this in more regulated environments where there are penalties or risk of life if systems go down? And I think the same sort of principles are going to apply, but we'll likely have to evolve the way that we do certification and conformance testing and so on. Hey, Jax, what is the maturity that Wind sees from AI deployments to the edge? So we regularly poll our customers on whether they're deploying AI. So what we find is that all of our customers across all industries have active research and development in AI. I haven't come across a single domain where AI isn't a focus for the development teams. Now, in terms of deployment, we don't see AI fully deployed in critical systems some broadly today. Now, there's some trials. I would say things like autonomous driving, for instance, is an application of AI in automotive. But there again, we haven't had fully certified, fully production models that have gone to mass market yet. So I'd say in terms of critical edge infrastructure, this is still relatively early, but I think it's coming and we need to be ready for that. So I see a question from Jack. I'm surprised that Wind River, a manufacturer of real-time software, endorses using Python in edge devices. That's almost as bad as suggesting JavaScript. So I think, Jack, you can be a purist, and we've been around a long time as a company, and we fully support C, C++, assembler, and very traditional ways of doing embedded development. And of course, we'll continue to support those. In fact, many of our customers are building embedded devices that are very critical. So I'm not saying that C, C++, and other things are going away. But if you look at how we need to enable productivity in embedded devices, we do see a need for modernization. And I view use of high-level languages of JavaScript or Python
as being another form of abstraction. You wouldn't necessarily write your control function in Python. It's likely not to be deterministic and so on. But you may want to add, some UX functions, some applications. So it's really about enabling that mixed mode of development. And so, we've got to go to where the market is and what developers need. And if you look at Stack Overflow surveys, for instance, you'll see that the availability of talent for high levels of abstraction is much, much more widely available than people with low-level C, C++ skills. So we need to be ready to adapt to that. So Steve, most of my market and prospects need to walk before they run. What solutions would you lead with to gain trust based upon results? So I think this is similar to the question that Don asked earlier, which is how do you see this approach being deployed in high availability systems? I think first you need to have, continue to prove out the viability of your base platform and methods. So I'm not suggesting that we can shift wholesale to good enough best efforts computing equipment. In fact, having a robust, solid foundation is paramount. But I think there are approaches which lend themselves well to validating systems before we deploy. So a lot of our customers are using high degrees of simulation, emulation, and hardware in the loop as they think about deploying those systems. So in the example that I've mentioned to Don, where we have a development and sort of release infrastructure, having the ability to have digital twins that are actually duplicating the overall environment is one approach that we see people take when they have much more critical embedded-like designs. So Umesh has a question about what are well-known edge software frameworks and any open source alternatives. So let me just clarify what I mean. When I use the term framework, I mean some sort of high level of abstraction. It could be a programming language, like I consider Python to be a framework. It's effectively a scripting interpreting language. Or the other thing that we see across industries is the notion of levels of abstraction at more at the middleware level, if you like. So if I think about automotive, there are moves towards standardization of system services across the vehicles, like adaptive AUTOSAR. Or if I think about aerospace and defense applications, you see interoperability standards like FACE. Or in oil and gas, there are efforts as well to have a common framework called the Open Process Automation Framework that will lead into standardizations. Now, a lot of those frameworks are actually open source. In fact, I'd argue that most frameworks to be successful need to be broadly adopted by communities of developers. And so, having proprietary frameworks is actually not the way to go. So I would say mostly we see the world evolve into frameworks being open, and in some cases being driven by standards as well. So let me read it out so that you can follow along with me. So Mary asked, is there a role for education and a good source for it to help developers and companies that want to transform but don't know how to start? Do we assume everyone who's smart enough to run a company also knows how and where to begin? Maybe just starting at the level of modern programming languages. Where does education in those come from? Are universities keeping up? So Mary, I actually think that's a great question. And I think actually universities are driving some of the change that we see ourselves need to adapt to. So, I'd made the comment earlier that higher level languages like Python and JavaScript and things need to be developed. And that's because at college these days, for example, you tend not to start at the operating system level, think about CPU architectures. We see a lot of students leave college with skills, programming skills at a higher level of abstraction. And so I think that's actually the right move. And what if I were to predict where we need to go, it's to fully embrace and harden those types of approaches that universities and other organizations are pioneering, and make them more adaptable to real-time robust environments. So as an example, there was a question earlier, and I think it was in jest, about whether JavaScript was suitable for the edge. There are universities in the US, for instance, that have real-time JavaScript that are more deterministic and are becoming more suitable for the edge. So the universities and academia are actually driving a lot of the changes that we need to adopt as commercial providers. And I think there's an awful lot that the education domain can do to help guide us as to where we need to be. After all, you are training the next generation of employees for us. So Steve, and I think this is Steve Jennings that I know. Hi. For example, on my previous question, I found if I can deliver cost savings in the short term, I can then recommend solutions that increase revenues, productivity, and improve the consumer experience. So I think, yeah, you've added to your response, Steve. I think you're absolutely right. I think having some form of tangible benefit with its ROI, time to market, robustness of consumer experience, these are all important things. So it can't all be things that we're driving for as developers that have no meaning in the real world. So you're absolutely right. You need to focus on the customer value. So question from Paul, is this new intelligent edge being applied in any smart cities that you know of? So it's interesting. You know, in the early days of IoT, smart cities were all the rage. And there were lots of initiatives that were tracking around deployment of smart cities. In fact, WinRiver at the time was deploying infrastructure for monitoring the environment, noise, pollution, and things like that in London. A lot of those, we've lost visibility of a lot of those initiatives, and I think the root cause has been not lack of technical interest, but really the business model around who is funding and monetizing the smart city efforts. So I'd say that the approach of a new intelligent edge, where you blend physical devices, cloud native, and applied DevSecOps, and the sort of paradigm you talked about, are absolutely applicable to smart cities. We're just not as involved day to day as with those initiatives anymore. Using mobile-first design of websites positively impacted usability. How did data-first paradigm impact user experience and hardware design? Now that's an interesting one. You know, we today don't necessarily see intelligent edge infrastructure be designed or architected for a data-first paradigm. I think when you do see that kind of approach, it tends to be at a very high level of abstraction. So using time-ordered databases and really more web-like methods. So I think you're starting to see that data centricity be applied to less critical applications because of that level of abstraction. And I think it really allows the user experience to be much more time-driven in terms of your ability to drill into data, to get insights from the applications you're monitoring. But it's hard for me to answer that question as to what the improvements have been, because by and large, I haven't seen pervasive rollout of data-centric architectures yet. So Don, thanks for your follow-up. And I think it's a comment that I'll read out, and I don't know whether other people can see all the questions, so I'll read it out. So I understand your comment about heterogeneity at the edge. However, the thought leaders should point the way towards standards for at least information models and communication protocols. I wholeheartedly agree, Don. That's why participation in things like the Open Process Automation Forum, FACE, Adaptive AutoSAR, and other things is the way for us as leaders and for the community to align, because using the right technologies is key, but defining the interfaces, the APIs, and the standardization of data models and so on is also necessary in order for these edge platforms to become much more usable and pervasive. So just a clarification from Mark, I think, is just to confirm you see data analytics taking place in the edge versus the cloud due to cost. And absolutely, I think well, cost is one aspect. I think given the explosion of sensors, devices, and so on, the volume of data being generated in a lot of applications is so huge. I go back to the experience that I mentioned earlier of us deploying intelligent infrastructure in Hyde Park in London, for instance. And the very first time my team had deployed there, we racked up mobile bills of thousands and thousands of dollars, and we had to quickly re-architect that. So, once you start turning on the ability to move data around, you quickly see that cost becomes a big driver, especially if you're using mobile networks as a backhaul. If you're physically or hardwired connected, it may not be as much of an issue, but cost is a factor. The other, frankly, things that I think are more important in many cases are around latency, robustness, autonomy of edge infrastructure, and frankly, being able to understand the context. If you're processing data in a particular device where you know what sensors are, the context of the sensors in their environment, you get a much richer ability to mine that data by applying that metadata and context, which often is lost when you move the data northbound. So cost is one thing, but I think there are many other reasons why we're seeing a move to the edge. And Mark follows on with, do you see over-the-air software standardization at the edge to reduce cost and complexity? Now, I would answer frankly that we don't see standardization yet. I think where we saw standardization was in classic mobile OTA type approaches, and we haven't seen that transfer to more generic edge infrastructure. Although there are technologies, in fact, there's no shortage of technologies to do OTA, frankly, but the standardization tends to be much more domain specific. And I haven't yet seen a group or initiative that is focusing on OTA more generically at the edge. Maybe that's something for the Linux Foundation or something else to work with, but I'm sure I can't fully answer that question. I guess me not knowing is an answer in itself. Let me read a question from David. So I found what you just presented fascinating. My question comes from a more practical standpoint. As these data-rich environments become more active, their energy requirements are going to become increasingly energy hungry. How do you therefore envisage powering your devices? And will you need to develop your own bespoke power generators? So I think here, I think you're right. If we just assume that we can apply more and more computing to the world, then energy demands are going to go up. But actually, what you see with more mature technology, I think of a mobile phone as a great example. A mobile phone now has, the computing capability of what was a laptop computer a few years ago, and the way they've been able to achieve that, yes, it's partly through process shrinkage and Moore's law. It's also partly due to highly optimized and hardware architectures, but at its core, the need for things like power management in those devices has become really key. So I'm not suggesting that we're going to turn on a smarter world of devices drawing more and more power. I think devices themselves are going to be much more intelligent, and they're going to have sleep modes and power consumption modes and so on, and that's where the scalability comes from. I think that's not only an issue at the edge for edge devices, but power consumption even in the data center, where quite often the data centers are located next to hydro plants and things like that for cheaper power generation. But even their power consumption is a major issue, and that has to be part of the overall infrastructure architecture that we consider. So Mark's followed up another question is, when do you see 5G being mainstream, and what role will 6G play? So, Wind River had really was very early in believing that the shift to 5G would happen, and I'd say that it's coming 6 or 7 years later than I really thought that it would happen. In fact, we invested in network functional virtualization and software-defined networking and some of these high availability, robust compute platforms. We did that early. The reality is that 5G is actually rolling out this year. I mean, as we speak, every carrier that we interact with worldwide is in full swing in terms of their 5G deployment. So as a consumer, you're just starting to see some regions be turned on. But behind the scenes, right now is when everything's happening. And as consumers, you'll see networks switched on, throughout this year and next year. The interesting thing for me for 5G, though, is when we start applying some of the characteristics that I talked about, the ultra low latency, high reliability, or the massive machine type communication, the scale. 5G isn't fully built out for all those use cases yet, but when that really happens, then I see 5G fundamentally changing the way critical infrastructure edge is defined, and not just the consumer mobility edge. So that's ongoing. And I'm sorry to say, Mark, but I'm not fully up to speed on the timelines around 6G. Yeah, Jack, I see a follow-on question, which is, but if everyone only knows the highest levels of abstraction, no one knows how to actually make the low levels of code that support the abstraction work. And I fully agree with you. I didn't mean to tweak you with abstraction. I'm just pointing out the general trend. In fact, one of the key dynamics I mentioned was the detail matters. So I'm kind of speaking out of both sides of my mouth here, which is we see developers and developer population want to move towards high level of abstraction because that gives them the productivity. They can ride on the shoulder of giants and reuse codes and things like that. But you're right, Jack, you absolutely need people who can delve into the difference of hardware, the differences of operating systems, understand make environments, tool chains, all that other goodness of embedded systems is really important. One thing, though, that I would point out is I often think of Moore's law and high level of abstraction really push in what I call the good enough. And as an embedded developer, we always started with, no, I had to design it from scratch because my real-time capability is too stringent, or I'm building a safety function. But what we see again and again is that notion of good enough, especially with higher orders of abstraction through tooling and standardization, really does become viable in more and more environments. It's not going to apply everywhere. If you have, a high-speed motor, for instance, in a safety-critical environment, I see that being ultra-tuned. But by and large, understanding, the characteristics of the environment that you build in is actually critical, and someone on your team has to do that. What I'm saying, though, is that there's a smaller and smaller population of people who are going to have to know that level of detail, and more and more people are going to be able to build things without starting from scratch. In fact, I read I've been tracking the low code, no code movement. That's become a bit of a buzzword in VC communities these days. And there's a very interesting project around, I think it's called a Twitter clone. A guy had set up a company who was able to, with no code tools, really recreate the whole infrastructure capability of Twitter. Now that's an example that you would rightly point out is more of sort of enterprise good enough type application, but it's hugely complex nonetheless. And so I'm just pointing to that as the kind of evolution in the way the market is going. Would you say, so Paul Samuel asked, would you say that latency reduction is the biggest driver to edge computing versus conventional cloud architecture? I'd answer that, Paul, by saying I'm biased because Wind River tends to serve customers who have critical needs, and quite often latency and timing characteristics are part of that critical need. So my viewpoint is time is one of those elements that has been completely ignored by mainstream computer science. If you look at desktop architectures, even mobile phone architectures, they're optimized for power performance or throughput or cost elements. Very few of them are optimized for timing elements. Now, I think that will change as we see things like autonomous driving are going to build sort of much more critical infrastructure requirements back on to the semiconductor community, and being able to manage critical timing, both at the software level and the hardware level, is going to become more and more important. Now, let's face it, the things like a real-time operating system, or being able to apply patches to Linux like PreemptRT, are really ways of managing capability that isn't being managed intrinsically by hardware. And when you look at ARM or Intel or other companies, you see that things like time sensitivity and applying TSN to their overall architectures are becoming more important. And at that point, the interesting thing will become, could I just apply a generic Linux workload and really rely on the capabilities of the underlying hardware to give me things like latency guarantees and timing guarantees. So I think that's a field that's evolving that's very interesting. So I'm going to take this one last question before we wrap. A gentleman named Dan Knoll. Pushing compute-heavy algorithms to the edge with AI and machine learning and others seems to be slightly at odds with the benefits of the cloud, e.g. security. Reductions in latencies that come with 5G and with cloud adopting accelerators like GPU, as you've indicated. What are the key drivers you see that will overcome these cloud benefits and drive more compute-heavy workloads to the edge? So Dan, I think you're right. If you look at the overall architecture and topology, a lot of benefits around security and other things have been built into the cloud, but you still have to move the data. One could argue whether you move the data or you just move the workload. What I actually see happening is that the cloud topologies are actually evolving to be deployed at the edge. So cloud today may actually be a physical data center somewhere up in Oregon or somewhere else. In the future, you're going to get local zones, regional zones, municipal zones. They're all going to actually be part of a common infrastructure. And the good thing about the way that cloud architectures have been designed is that that location of whether you're running on one core in a data center on the East Coast or a physical device on the West Coast or wherever really doesn't matter. So I would actually argue that the cloud is going to become more pervasive to include being deployed distributed at the edge. And so the notion of what cloud is not going to mean data center in the future. It's actually going to be that much more broad-based definition that includes the edge itself. So we're at the top of the hour, and I really appreciate all of the questions you guys have asked and for your time and participation today. There's, I meant on this slide, there's a landing page where you can download a white paper with facts and references that I've been talking about. And if at any point you want to reach out, feel free to do so. Thanks for your time today.